Today presentation I have is modernizing the approach to in situ chemical oxidation by eliminating the need for chemicals. Quick outline on the presentation, do an introduction on Provectus as a company, discuss the Provect EBR technology and case study, supporting case study information on the system. And I will be back obviously at the end after Mitch's presentation for our Q&A session. If you have questions as I go through, as Tim indicated, please type those in, indicate that question is for me, and we will address them here at the end during the Q&A session. So as a background on Provectus as a company, we were formed in 2014 on acquisition, utilization on patents on ISCO, ISCO, and methane inhibition. We are a technology provider, not a field service provider. If turnkey projects are required, we partner with various both national and international implementation companies for turnkey design if that's required. My colleagues and I come from both consulting, remediation contracting, and product and technology developments. So this is a general animation that I like to start all of my presentations with. It's somewhat of the approach that we take in trying to work with the subsurface that we're working in with all of our projects. The better knowledge and understanding we have of the site and its natural conditions allows us to better select and implement the correct technologies and working within that site geochemistry instead of trying to work against it or force it into a direction it's not naturally going to go. So the need for new technology really stems from the limitations, the natural limitations that we see in situ chemical oxidation. Longevity, if any time you're dealing with any oxidants that generate reactive oxygen species or the radicals, longevity here is the biggest issue. They typically have environmental reactive half-lives in the micro or sub-microseconds, and that requires the need for them to be continuously generated or additional chemistries applied to sustain those reactions. One of the other applications we're always looking at is being able to do a PRB application with in situ chemical oxidation. There have been various technologies where we've seen some improvement, use of potassium-based oxidants, for instance. I know Karis had talked about that earlier today with the potassium permanganate. It has a lower solubility, so extended release time, so that helps. But typically, if you compare that to in situ chemical reduction PRBs, those typically use technologies and chemistries that can last, 18 to 24 months. So being able to bring a chemical oxidation technology that has that sort of longevity would certainly be beneficial. And then obviously going after those areas that are difficult for traditional in situ chemical oxidation, recalcitrant compounds, the 1,4s, MTBE, or perchlorates, deep aquifers, that certainly would be a challenging application. Trying to get 80, 100, 120, 50 feet below surface would be difficult with traditional ISCO, as well as challenging lithologies, those tight clays and silts, which might make that difficult. So the one thing that we're always looking at is, am I generating a reactive enough environment to treat the chemistries that need to be remediated? This is a quick chart of general oxidative chemistries that are available in the market, and you see the most reactive of those are these reactive oxygen species, those hydroxyl radicals, the persulfate radical species. These are our more reactive. That allows us to go after those contaminants that have higher bond energies. You can see like permanganates down toward the bottom with a lower oxidation potential, which allows it to treat things like the chlorinated ethenes. That substituted carbon-carbon double bond has a lower bond energy, which allows that to be effective there, but not so much on like the BTEX compounds, which have higher bond energies. in which case we need something that's a lot more reactive. So in light of those needs and restrictions, we're looking at a different type of technology with the Provect EBR. This technology is, from the most basic understanding, is the ability to generate elemental oxygen, convert that oxygen to hydrogen peroxide in the presence of continuous ferrous iron release. On this slide, you see the primary components of the system. The photo on the left, on the lower left, is a portion or a snapshot of part of the control panel that monitors and maintains the system. The photo on the lower right are the two downhole components of the system. In the foreground, you see the EBR reactor, and in the background, you see the sacrificial iron electrode. That electrode has a specific current density that's applied to it to increase the rate of oxidation and release of iron particle. And the reactor in the foreground has the cathodic and catalytic surfaces, which facilitate the generation of the elemental oxygen and conversion to hydrogen peroxide. The photo on the top is one of the real interesting things with this technology. This is a snapshot of the control panel where the system is monitored and maintained in real time. Anywhere that you can log on, you have internet access. The system is communicating through cellular networks. So anywhere we have a site with reasonable cellular service, the system can be connected, and we can monitor the effectiveness in how the system is operating and make any adjustments that may be needed anywhere remotely without having to actually travel to the site to make any adjustments that would be required. This is a patented technology with the Elgresi Group out of Netanya, Israel. It's patented both in the United States as well as in Europe, and Provectus has exclusive license with the Elgresi Group to provide this technology in North America, most of Europe, and Southeast Asia as well. So how the EBR system works. If you're familiar at all with electrophens generation, the base concepts are somewhat similar. Those have been described in various publications over the years. On the photo on the top right, you actually see the EBR reactor itself in a tank of water. And if you look closely enough, you can see that effervescence. That's the generation of that elemental oxygen that occurs on the catalytic surface of the reactor, where it undergoes that reduction of water to molecular oxygen. This is a key point to the technology in that this is a saturated zone technology. The reactor and electrode need to continuously be exposed to groundwater. This is not a vadose zone technology. So when deploying the reactors and electrodes, you need to be aware of depth to groundwater and where these are being placed in relation to that depth so that they're continuously exposed to site groundwater. Then on the cathodic surface of the EBR reactor, it undergoes, you see that elemental oxygen undergo a 2-electron reduction to generate that hydrogen peroxide. Again, with that sacrificial iron electrode and the current densities that are passed through there, that ferrous iron particle is generated and released and interacts with that hydrogen peroxide. And in typical Fenton's chemistry fashion, you see the formation of those reactive oxygen species, the hydroperoxyl radical, the superoxide, as well as the hydroxyls. Depending on site chemistries, we may also be able to generate ferrates, which would be iron in the +4 to +6 valence state, which are also very, very reactive as well. On the lower right, you see a list of propagation reactions. This is the portion of the chemistry and the science behind the system that allows us to generate these reactive species radially outward from the reactor points themselves. It's a continuous formation of the reactive oxygen species back to the components to then form the hydrogen peroxide. The iron 2 and iron 3 undergoes a Haber-Weiss type reaction where it trades that electron back and forth from iron 2 to iron 3 to restart the reactions again outward in the subsurface from the reactor points themselves. So how this differs from an electrophoresis generation is the ability to form these iron 2, iron 3 nanoclusters. Again, this is that shuttling of an electron back and forth, creating both iron 2 and iron 3 in sequential fashion in these propagation reactions. These are small, about 2 nanometers in size, which are formed again through that corrosion of the sacrificial iron electrode. And at the higher ORPs that the system's able to generate, typically over 550, 600 millivolts, it generates these low-level Fermi wave fronts, which sets up a thermodynamic differential to allow the formation of these redox fronts that move radially outward from each one of the EBR reactors. If you use a mesh network type Wi-Fi system at your house or your office where there's various pods that intercommunicate with each other, it's similar in concept with the various EBR reactors on site. They each emit out these redox front waves of increasing reactivity, and as those wave fronts come together, you form that mesh which would allow us to set this up as like a PRB boundary, or to fully and completely treat a source area. There's other chemistries that come into play here with electroosmosis and electrophoresis. That's a lot more detailed scientific explanation than this presentation would allow. But the system does allow for modulation of the voltage and amperage to each one of the reactors to allow for dynamic coupling between each of the EBR wells, so they work in synchronicity with each other to accelerate the formation and coupling of these various wavefronts. So again, summary on the reactions. The primary thing is the generation of hydrogen peroxide in that atmosphere and continual exposure to the +2 iron to generate those reactive oxygen species. And again, through those redox fronts and thermodynamic differentials, literally propagate this outward in a true radial fashion, both laterally as well as vertically. Once the system is shut down and we've concluded operations, the system would transition from an ISCO atmosphere to a bioremediation using that oxygen and remaining iron that's distributed out through the area as electron acceptors. And again, this system and the operation is controlled remotely, real time through it's a partnership we have with Mitchell in the Field Data Solution Group. Mitch will be speaking here after I complete, but utilizing their platform, we're able to monitor this in true real time and make any adjustments that might be needed. So system design, the system can be either set up fixed. Typically, you can see this deployed at a active fueling station or a gas station that may have groundwater impacts from a leaking, fuel leaks. BTEX, MTBE typically are the contaminants we see there. So we can fix this control panel right at the fueling station and then trench out to the various points where the EBR reactors would be located. Or if the system or the site is more remote, we can mobilize it. And in the photo in the middle at the bottom, you can see the control panel located within the EBR trailer. The photo on the bottom right is actually from our most recent pilot testing, where we went from phase 1 to phase 2. and we were setting everything up for the phase 2 operation, actually communicating directly with our colleagues in Israel to do setup and calibrations and bring the system online. So there you can see a little more detail of the inside of the control panel that drives the system. That's actually the controller that I'm working with at that point to set our calibration points for upper and lower limits on voltages and amperages, and we can set up alerts to critical people on the project team to be alerted if we exceed or fall below predetermined upper and lower limits for voltage and amperages. So where the system's been used, in 2021, Israel had 35 gas stations that were undergoing active remediation, which may not seem a whole lot, but when you contemplate the fact that the country of Israel has the landmass of about the state of Vermont, it's a reasonable number. The EBR technology was deployed at 14 of those sites, plus at 2 chlorinated solvent sites. And of those, 7 of those 14 today are in clean closure status with ongoing monitoring after 1 year of operation at those sites. It's an ISO certified technology that's approved and recommended through the Israeli Water Authority, which is somewhat similar in operation to the US EPA. So if there's a fuel station site that has impacts that are threatening groundwater, their recommended approach is to utilize this EBR technology. Here in the US, we've deployed this in a PRB application for an industrial landfill in the eastern United States, and we are continuing evaluation of a completed pilot project and proof of concept project in the Midwest for benzene groundwater and soil treatment that will be the focus of a case study that we'll go over here. This pilot test, again, this was a historic benzene release. Fairly shallow impacts at this site, 13 to 20 feet below surface, so not terribly deep, but very, very tight natural clay lithology. Groundwater movement is negligible here. It's in the centimeters per year, so there's not substantial groundwater movement at all. The pilot test was broken up into 2 phases. Phase 1 was in an unfractured area, and phase 2 was in an area that had previously been fractured for potential deployment of an SVE system. So this allows us to compare what occurs when the site lithology has been fractured compared to just natural conditions of the soil. That phase 1 in the unfractured area was started on June 6th of 2023, and we completed that on 15 September of 2023. In that area, our background benzene groundwater concentrations were substantially high. We were 640 to 850 part per million of benzene. And our background soil concentrations were between 1,100 and 2,600 milligrams per kilogram. Our goals here were obviously to reduce groundwater concentrations as much as possible. And the ultimate goal for treating soils would be to get below 400 milligram per kilogram to consider it properly treated. So the design in the unfractured area, the layout of our system is here. The red boxes marked EBR U1 through U4 are the 4 points where the reactors were deployed. The monitoring wells are marked with the blue dots are GP 216 through 220. You can see 3 of those monitoring wells were located within the perimeter, so to speak, of our 4 EBR points. The EBR wells were located about 22 feet spacing between each. So we anticipate over time as the system works and continues to operate that those radial influences will overlap. And we also had 6 piezometer wells marked here UP1 through UP6. These were 1-inch wells that we could pull and sample, and we did that on a weekly basis to sample both geochemistry and also our contaminant levels in groundwater. So baseline starting results, and after 3 months of operation, not surprisingly, we saw increases in conductivity from the release of that iron through the subsurface, we would expect our conductivity to go up. Groundwater pH, again, here we're looking for maintaining of circumneutral pH. We did have one well outerlying the GP 217, actually started with a fairly high pH. We think that was influenced from a subsurface holding area that had been backfilled with material that was driving that pH up. But at the end of that high pH actually had brought itself back down to 7.6. One of the interesting things with this technology is the low energy consumption and cost. Our average daily energy usage here to run the system in phase 1 was about 31 kilowatts per day. Based on consumer energy cost in that area of 20 cents per kilowatt, it cost us about $6 a day to run the system, so very, very economical. So our reductions, again, our baseline here when we started, our groundwater baseline levels were between 640,000 ppb to 850,000 ppb. Again, we were taking samples weekly and testing, and in our EBR wells, we saw reductions of 99%, almost 100% reduction within our EBR wells. The 3 monitoring wells within that perimeter, again, we see 91 to 98% reduction, and significant reductions obviously in our piezometer wells as well. The 2 monitoring wells that were outside of our perimeter, again, these are being influenced by a single reactor only, but between 50 and 60% reductions in groundwater contamination at those points as well. So, baseline, looking at sampling we did 40 days post shutdown, the EBR wells, again, our average was about 650 part per million. Our average at completion was 2.7, so 99.5% reduction, again, after 90 days. Monitoring wells average 73% reduction, and the piezometers, our 1-inch wells, about 81%. 40 days after operation, we were able to get ground or soil samples taken and analyzed right in near our EBR wells, the reactor wells. We saw about 90% reduction. The monitoring wells out to that distance, we saw no change at that point, but our piezometer wells had showed almost 60% reduction in soil contamination as well. So we know the system just needed to operate longer. Again, this was a proof of concept and functionality. We know to achieve true cleanup, the system would have to operate longer than 90 days. So from there, you can see the various soil data at both the EBR wells and our monitoring wells, both at the depth of where our reactors were. We expected to see rebound because these samples were taken 60 days after the system was shut down. So these results were as expected and confirmed to us the system did operate as anticipated. It would just need to run a longer period of time. On to phase 2, again, this is the fractured area. The system was deployed in a linear fashion with the EBR reactors as F1, F2, F3, and F4 in a true linear pattern, with monitoring wells between EBR 1 and 2, as well as between 2 and 3, and then 3 outlier, so to speak, monitoring points, and our piezometer, our 1-inch piezometer wells located around EBR 4 for our sampling and testing. In the phase 2, in the fractured area, you see one thing obviously we're tracking and testing is that ORP, and you see significant increases in the ORP and benzene levels in groundwater. Again, within our EBR wells, 98% reduction. Our piezometer wells around EBR 4, almost 90%. We were just beginning to see impacts out to the distances of our monitoring wells when the 90-day operation stopped. So the steps yet to be completed is data evaluation and determination of that time value and how long the system needs to operate, and if there is a functional difference substantial enough in the fractured zone to the unfractured zone to validate the use of doing additional fracturing throughout the rest of the plume area that needs to be treated yet. Appreciate everybody's attention on the project. My contact information's here.